guys, we're going to start talking about vectors and some parametric equations throughout this chapter. First thing we're going to start getting into in 8.1 is geometric vectors. Okay? So a vector is basically anything that's going to have distance and what?
Direction.
Geometrically, a vector is represented by a ray. Now, guys, a ray would mean that this goes on forever. Okay? The only thing that this ray is really showing you is what direction it's going. So as an example right here, this vector basically starts here. Okay? So there would really be a starting point right here. It's moving this direction by the arrow, but technically it's not going on forever. It actually ends there. The only thing this arrow at the end of this ray is showing you really is what? Direction. Okay? So it would kind of be a line segment, but if it was just a line segment right there, Amy, the question would become, what direction is it going? Right? So that arrow at the end tells you this is kind of where we're starting, moving this direction to get to that end. Okay? So I'm sure you've talked a little bit about maybe magnitude and direction in some science classes before, but the length of the vector is going to be called what?
Magnitude.
So if I told you this was like 12 feet up here, again, we measure distances as positive distances only, so we represent the magnitude by the absolute value of your vector v. In this case, the vector would have a magnitude of how many feet here, kids? 12 feet. Okay? Now the thing you're going to start talking about a lot is this. And you don't have a sheet of paper for this, but I think this will make pretty good sense to you. A vector is going to be in standard position when it has its initial point at the what?
Coordinate.
Okay. If I go to the coordinate plane like this, okay, this would be considered a vector in, let me do this. This would be considered a vector in standard position if I went like that. Okay? That would be considered in standard position because its start is where, kids?
Origin.
It's at the origin right there. I'll get it right there at the beginning. Now, kids, you're going to hear a lot today, all right, about some things in terms of vectors and standard positions, all right? Part of your assignment that you get on Monday is going to start asking you about some of separate vectors, okay? How many of you guys have flown on an airplane before, okay? When you've flown before, there's always a path that the plane takes, but does the plane always fly in weather that's great, or does it sometimes go through weather that's bad? Sometimes there's bad weather and it might be windy. So you might have a plane that wants to go this way, but a wind that's pushing it this way. Is it going to stay on path if that wind's pushing it? No. So what we talk about is where's the plane's resultant going to be if I go a certain direction and I have wind pushing it. And you're going to hear us talk about adding vectors and something like this. So here's the deal that you're really going to see. You might have two vectors, one here and one here. I don't know, like this. And maybe I call this vector right here A. Maybe this is vector B right here. You're going to get asked questions like, what is vector A plus vector B? What's the resultant of A plus B? The thing you just need to remember about it is this. When you sketch these, a resultant vectors is like taking the first vector listed and adding the second one. So you're always looking at this right here. The ends with the arrows are called the tails. Okay? And I like to call the beginning here the lead. And what you always do is you put the lead of the second vector on the tail to see where things result. So let's say that a plane needed to fly on this vector B right here, but a wind was pushing it at vector A. Where would that end up at? Okay. Well, guys, to know what A plus B is, we got to take the vector tail and put it with a vector lead. So in other words, A plus B, A is listed here first, right, kids? Isn't A right there? Okay, if I would take B then and take B's vector in standard position and put it at the tail of A, the combination of these two vectors right here would put you as a resultant vector. Well, that's pretty cool. That worked out. The resultant vector would be right up here. And this vector right here would have been that vector right there. That's dotted like that. This here would be the result of those two things put together. Okay? Does that make sense to you when you start talking about adding vectors in and sketching what they would look like again? Okay? Okay. Same thing too, kids. Let me show you this. The order could have gone the same on this. I could have taken, this one was down here originally, wasn't it? I think so. Look where this ends up if I put these together. Kind of the same spot again, doesn't it? Okay, so if I ask you to take two vectors and add them up, can you at least sketch them for me? See what it would look like there as a resultant vector? You guys cool with that? All right. Let's see. All right, well, let's head back here to that other page. So things to think about today. The length of the vector is going to be called what again, kids? Magnitude. Okay. We know a vector in standard position has initial point at what? Everything that we've talked about in Trig this year has always had like a terminal side start at the origin, hasn't it, kids? So it's kind of similar to what we've talked about. Now, something that might be kind of new for you is this. We've talked about amplitude relative to writing trig functions in the past. In terms of geometric vectors, the amplitude of a vector is going to be the angle that's made with the, and this is a biggie, positive x-axis right here. Okay. So if I go back to my drawing right here, kids, if I go back to my drawing here, like look at vector B right here. B is right here. Okay. The angle formed with the positive x-axis meaning going to the right on the horizontal. The angle that's formed right here, kids, this here is called your amplitude now. So you're basically saying, what's that angle that we have? What's that angle that we have formed with the x-axis? Very similar to like everything we've done so far, right, this year? We just have a new name for it now. And what's that called? Amplitude, you bet. Okay. All right, so there's some terms there that I think that you kind of know them. They're just going to be referred to a little bit differently. Okay. So recall this. Have you guys talked about polar form before? Have you seen polar graph paper before? Have you seen graph paper that looks like this? No, we've got to be more open than just this. Have you seen graph paper that looks like that before? Never? Okay. This is called polar graph paper. All right. And you're going to start seeing some things that show up in polar graph paper that say, we want to go ahead and graph the point, say, I don't know, like 4, 30 degrees. Okay. Polar coordinates, sorry, my phone's ringing. Polar coordinates, according to your notes, are always written in the form r, theta. Okay? R is going to basically stand for the radius. How far out am I moving from the center? So if I had a point like 4 here, kids, I would move out how many rings? 1, 2, 3, 4. All right, now my friends, each one of these sections is 15 degrees here in this polar graph paper. I'll just tell you that. What it says then is rotate how many degrees after that once you've gotten out here on a radius of 4 or out to the 4th ring. So 30 degrees would be right here. This would be that point, 4, 30. Okay, 4, 30. Now the thing that they talk about, kids, is this. This is going to be the vector that would be formed by graphing something like 4, 30 in polar graph paper. Now, we're not used to this graph paper. We're used to what type of graph paper all the time, kids? Like that. And we're going to talk about, okay, what would coordinates in a polar graph look like as coordinates in a standard coordinate plane? Okay, so instead of giving like a radius and then an angle, we want to give like a point, 5, 7 in terms of x, y. And there's a way to do that. And let me show you how that's going to work here today. So, sorry guys. I know who's calling. And they can just leave a voicemail. All right, so in standard position, vectors are going to have a magnitude and an amplitude. We've already talked about that, written as magnitude, amplitude. And this is going to be kind of in a polar form, where r is going to represent a radius and theta is going to represent an angle. Now, in rectangular form, back to a coordinate plane, we would always like to list them as an x, y coordinate. Draw a line from the origin to that coordinate. And here's how we're going to change this here, kids. Okay? Since we're dealing with the same components in the past, just now we're going to be calling them different names. So r is going to stand for what again, kids?
Radius.
Theta is going to be your typically measured in degrees, okay? And that's going to be called your, so the radius is going to move to what?
Magnitude.
And the angle is going to move to, you know this, all right? It says right here, my friends, x and y will be called horizontal and vertical components, okay? These two types of measurements right here, typically used in polar graph paper. Okay? X and y components, these are going to be used in coordinate planes. Okay? And then the question is going to become, if I have a certain polar coordinate, what is that coordinate in a coordinate plane, or as vertical and horizontal components, if you will? If I have polar coordinates, what are they as vertical and horizontal components? So let's jump into that. Let's see what that looks like. So at the top of the next page, or the last page, if you will, here, they talk about this. They say, suppose you are given what form, kids? In polar form. Okay, so you're given a radius and theta. Back on that example I was using, I used the point 4, comma 30 degrees. All right. The question becomes this. If you want to change polar coordinates into rectangular coordinates or vertical and horizontal components, here are your formulas. The x value becomes r times what, kids? Okay, so 4, comma 30 degrees in polar form, which is this point right up here, okay, would become the following in rectangular coordinates, okay? The x value is found by taking r, which is 4 times the cosine of what? So x comma y is going to become the following. It's going to become 4 cosine of 30. And then what's y going to become according to this? 4 sine 30, right? All right, I need your help, kiddos. In your calculator, I need to know what 4 cosine 30 is. I think I know it, but I'm going to check one.
3.4641.
3.4641. So I'm going to call about 3.46. Is that okay, kids?
Mm-hmm.
Okay, somebody do 4 sine 30.
210.
Okay, so here's the deal. If I had a polar coordinate, 4 comma 30 degrees, to put this in rectangular coordinates, that angle or that point would be 3.46 comma what?
2.
Okay, I want to show you something real quickly. I'm going to go back to my coordinate plane. Get rid of all of this. Friends, what was that point again about? 3.46 comma what?
2.
So about 3.5 and up 2. So somewhere about here. If I would go ahead and draw a vector right here, like this. Let's see how lucky we can get with this here, all right? What angle were we working with in polar graph paper? A little bit of luck, that angle should be how many degrees there, kids?
30.
Do this for me. You guys got your calculator handy? Do 3.46 squared plus 2 squared. 3.46 squared plus 2 squared.
15.9716.
Now take the square root of that. So given some rounding in here, we're pretty gosh darn close to what value?
4.
What was the radius in the polar graph? 4. Does it make sense that this distance is 4 right here, kids? Okay, a little bit of luck. Let me just check something real quickly. A little bit of luck. What angle should this be? What point were we working with originally, kids?
4.30.
I'm going to try something here quickly and see if this works out. Come on. What do you think, kids? Are we pretty darn close there? Okay. If I have a polar coordinate, r comma theta, how do you find the x value for a rectangle? What's the formula? R cosine theta, where r represents your
X.
x value, or in case of that, your r is going to be your radius. Okay, and then how do you find the y value at this point up here?
R sine.
R sine
Theta.
theta. Okay, all right. So if they're going to say go from polar to coordinate, a rectangular form right here, then they're probably going to say go from rectangular back to what? Okay, and so here's how this is going to work for you, kids. And this is pretty simple too. Just reading through this. This is going to say, given rectangular form, it's time to change to polar form. So here's how you're going to do this. Suppose I have a rectangular form of the point, let's go 8 comma 6. Is that fair, friends? So in rectangular form, I have 8 comma 6. And it says you want to turn that to polar form. You want to turn it to polar form, which would be something like r comma theta. So up here it says your formulas for the following are here. I don't like the order they wrote these in. I might put a little like this to switch them around, because you really should list the r value first. Okay? So to find the radius, it says it's the square root of x squared plus y squared. It's basically the Pythagorean theorem. We're looking for a radius, or a hypotenuse, if you will. So what's 8 squared going to be, kids? 64. What's 6 squared going to be? 36. So 10, you're saying? Okay. Then the other part for theta, it says do the tangent inverse of what over what?
Y over X.
Okay. So it'll be the tangent inverse of what values over each other? 6 over 8. Tangent inverse 6 over 8. So run that for me, kids.
I don't know if
136 point.
Oh, it's like that.
What'd you get for an angle?
36.87.
I like that. 36.87. I'll call it 36.9 degrees. Is that okay? Okay. So quick question, kids. Up here, if I give you an example, it says start with polar coordinates. Can you turn them back into rectangular coordinates down here? Using the info up here. If I say start with something rectangular, can you use these formulas to put it into polar form right here? Are you okay with that? Okay. So let's practice adding vectors in polar form. Okay, adding vectors in polar form may not be as easy as just adding stuff up. Okay, typically we add vectors in rectangular form and then convert them back to polar form. So the first thing I want to do is convert these two. Okay, these are both in polar form to start, right? Let's convert both of these to rectangular form. Okay, when you have rectangular form, you can easily add stuff up. Okay? So help me out, friends. Wouldn't I do 3 cosine 50 and 3 sine 50 for this? Get that in rectangular form right there? Okay, somebody do 3 cosine 50. Who's going to volunteer that?
I got it.
Okay, and somebody do 3 sine 50 for me.
I got it.
Okay. When you've got the 3 cosine 50, tell me what you have.
1.928.
1.928, so I'm going to call it 1.93, comma, how about the r sine theta?
2.29.
Okay, and then that's going to become, we got to do the same thing here, 4 cosine 210 and 4 sine 210. Who's got 4 cosine 210?
Negative 3.46.
And who's got
It's negative
-2? Okay. Once you get stuff into rectangular form like that, we can easily add them up. We'll add the x's and add the y's to get a resultant vector, and then we'll put that back in polar form here. So the result on this here, kids, I'm going to make some room here. Just give me a second. Okay, so the result on this then, help me add these up. Kids, 1.93 and negative 3.46.
Negative 1.53.
Negative 1.53, comma.
0.29.
Okay. Now, is that in rectangular form? Is that a rectangular form sum, or is that a polar form sum? That's a rectangular form sum. So put this all in polar coordinates now. I'm going to write down this is an R sum for rectangular sum. We now want to get back to a polar sum. Okay, kids, how do you find the radius again?
The square root of it.
Yeah, so we got to go negative 1.53 squared plus 0.29 squared. Keep in mind, when I square this negative 1.53, what kind of value will that become? Yep. Okay, so when I add them up and then square root this, kids, I'm getting about, we need like 1.557. How about you guys? I think you forgot to put parentheses around that negative number before you squared it.
Yeah.
And I'm getting 1 point, can I call it 1.56? Is that okay with you guys?
Yep.
Okay. All right, and then to get the theta here, how many degrees we rotate around, we've got to turn that into tangent inverse of y over x. So if I go tangent inverse in my calculator, second tangent inverse, and it would be, what's the y value in our rectangular sum? 0.29
Yeah.
over what?
Negative 1.53.
Oh, yeah, that's right, negative 1.53. Kids, I get negative 10.73, which would be negative 10.73 degrees. Okay? Let me ask a question. When I threw these coordinates right up here, did you just think it was going to be 7, 260?
Yep.
Okay. Polar coordinates are weird. You can add vectors in rectangular coordinates and get away with it. So if I had a point in rectangular coordinates that said, take 3, 4 and add negative 2, 7. What's 3 plus negative 2? 1. What's 4 plus 7? You would end up at the point 1, 11 when you add those two vectors. Okay? However, in polar coordinates, you cannot do a polar sum by just adding them together. You need to convert stuff into what first? Rectangular form, and then do your rectangular sum, and then convert them back to what? Polars. Okay, so let's do this. Let's try one more here before we head to lunch here. Help me get these 2 points in rectangular form. So 8, 30 and 4, 30. 6.93, comma.
4.
And that's going to get added to, what's 4, 30 going to be? 3.46. Did you say 2 for the next one?
Yeah.
I agree with that. Okay. So there's a conversion of polar points to rectangular points. Now we can add them. So somebody do the 6.93 plus 3.46. 10.39, comma 6. Okay, so now, my friends, we're going to say that would be where the resultant is with stuff in rectangular form. That's where the two put together end up at. So to end here today, kids, we got to put that back in what form? Okay, so the first part's your radius. That's just 10.39 squared plus 6 squared, and then root that out. I'm hoping you get something kind of close to 12 there. 11.9-ish. So I'm going to round it up to 12, okay? And I'm going to show you why I'm going to call it 12 here in a second. Okay. Tangent inverse of 6 over what?
10.39.
I get 30. Oh my gosh. Okay, 12 comma 30 is kind of what we end up with. All right. I'm going to go back to my polar graph paper and show you why this kind of works. And then when we get back from lunch, I'm just going to have you make sure you're good with this. Just check this on your own, and we'll call today a day if you guys are okay with that. You guys have everything down here first. Okay. Let's go back to our polar graph paper and take a look. I'm going to use this example right here. So what did you notice about the angles in those two coordinates?
It was the same.
They were exactly the same. So what it's kind of like saying is this, kids. I'm just going to pick on a point 1 comma 45 and 2 comma 45. Think about this. 1 comma 45 means go out one ring and go here. That's that vector. Okay, and then 2 comma 45, go out 2. That would be this vector right here. Okay? Well, if I take the two of those and add them together, take the lead of one and put it at the tail of the other, where does that end up at?
3,
They're both going the same direction, doesn't it? Okay? So if you ever see you've got the same angle out here, then you can add them together. All right? Because this ends up, how many rings out, kids? 3. And then what angle again? 45 degrees. And take a look at this right here. The thing that you might notice is like, ooh, in polar coordinates, what was true about these angles right here?
They're the same.
If your angles are the same in polar coordinates, guess what, my friends?
We just.
You can get away with adding. All right? So maybe make that note there. All right? Kids, that's what I've got today. When we get back, we'll try this last one on your own. Questions today?